Okay, thanks for the invitation to speak here. So today I'm going to speak about joint work with Frédéric Naud and Doron Puder. Frédéric's in Paris and Doron's at Tel Aviv. Okay, so the theme of the talk is spectral gap. I designed the talk to be accessible to graduate students, basically, so things may be quite simple for a while. I'll try to get into some details of the proof at the end. If you have any questions, please interrupt me and ask. And I want to apologize to people who have seen my Zurich talk, yeah, because it's like essentially the same. Okay, so let's start by talking about spectral gap. So spectral gap shows up in many different areas of mathematics. In this talk, I want to focus on two notions of spectral gap. So eventually I'm going to talk about spectral gap on surface, but many of the questions there are motivated by questions about graphs. So I want to start by talking about the spectral gap of a graph. Okay, so let's do this. Graphs. This is misbehaving. Okay, so what kind of graphs am I interested in? I'm interested in d-regular graphs. Sorry. I do have a backup if this doesn't work. D-regular graph on n vertices. Okay, to draw a picture of what I mean. Here's a 2-regular graph on 3 vertices. And if you have such a graph, you can form its adjacency matrix, which is a n by n matrix where the rows and columns are indexed by the vertices of the graph, and there's a 1 in ijth position if there's an edge between vertex I and vertex j. So for example, for this graph, there are 3 vertices. No vertex has got an edge from it to itself, so there are zeros on the diagonal. And every pair of distinct vertices is connected, so there are 1s off the diagonal. So the adjacency matrix is always a real symmetric matrix, so it has real eigenvalues. So let's write them down. The largest eigenvalue is always actually equal to d. So I'll call that lambda 0. And then I'll order them in descending order. Okay, so there are n eigenvalues. And it doesn't matter for this talk, but the smallest eigenvalue can't be any smaller than minus d. So this collection of eigenvalues, it's just the eigenvalues of the matrix, but I'll call it the spectrum. So the spec of AG. So that's the spectrum. What's the spectral gap? Well, the spectral gap is the gap between the lambda 0 and lambda 1. So it's lambda 0 minus lambda 1. And it tells you various things about the graph. So here I wrote non-strict inequality. So first of all, this could be 0, but this happens if and only if the graph is connected. Oh, sorry, if and only if G is disconnected. So if the spectral gap is positive, the graph is connected. Actually, it turns out that the size of the spectral gap tells you how highly connected the graph is. So lambda 0 minus lambda 1 quantifies the connectivity of the graph. That's a result of a law and Neumann. And it also has a dynamical application. So the spectral gap tells you how fast. So if you do random walk on the graph, starting at some initial vertex, tells you how fast a random walk converges to the uniform distribution. So it quantifies the connectivity of G and the exponential rate of mixing of random walk. So both these properties, high connectivity and random walk having fast rate of mixing, have like many applications in practice. But there's a contest. So you want your graph to be highly connected, but actually maybe in your application there's a cost for each edge. So you want your graph to be sparse. That's what D-regular graphs are. So if you fix D and the n go to infinity, you get a very sparse graph. And there's a contest, there's an obvious conflict between these two things, like having very few edges and having high connectivity. And so the challenge is to construct D-regular graphs for D fixed with a large number of vertices with spectral gap bounded away from zero. Okay. Okay, so now that we talk about spectral gap of surfaces, and particularly hyperbolic surfaces. What is a hyperbolic surface? Well, I'll explain how you construct them. You start with the hyperbolic plane. So it's a collection of x plus iy, but the x and y are real numbers and y is positive. So this is the upper half plane, and it comes with a metric, hyperbolic metric, which is dx squared plus dy squared over y squared, which makes it into a Riemannian surface. Because you have this Riemannian metric, you also have a volume form or a measure. d mu is dx wedge dy on y squared. And to define the spectrum, you also have a Laplacian, which is minus y squared dx squared plus dy squared. Okay, so this is a Riemannian surface with a Laplacian, but it's not a very interesting surface because it's homeomorphic to an open disk. So to get something more interesting, you take a discrete subgroup of PSL2R. I want gamma to be discrete and torsion free. Let's just say it's finitely generated as well. Okay, and then, okay, so PSL2R acts on the upper half plane by isometries via Mobius transformations. So I can quotient, I can take H mod gamma, call it X. And all these objects, the metric, the measure, and the Laplacian descend to corresponding objects on X because they're invariant into the gamma. So X is my connected hyperbolic surface. So that's my definition of a connected hyperbolic surface, something that arises in this way. Now, at some point of the talk, I may have to talk about surfaces that are not connected. But if I talk about a hyperbolic surface that's not connected, it means it's a finite union of these things. Okay, so this surface X is supposed to be analogous to a graph from the previous page. So I want some analog of the adjacency operator, and that's going to be given by the Laplacian. So this Laplacian on the hyperbolic upper half plane is invariant under gamma, and so it descends to a differential operator on X. So like a priori, it just acts on functions with enough regularity. But by functional analysis, it extends to an unbounded self-adjoint non-negative operator on L2. Which we'll also call delta x on L2 of x. Okay, so there's something you can do with such an operator, which is to spectrally decompose it. So in general, spectral decomposition of unbounded self-adjoint operators should be thought of as a projection valued measure. So let's do this on the next page. But if x is compact, which I'll now ask, this takes a nice form. Namely, it's parallel to what happens for graphs. The spectrum is discrete. So if x is compact, then I'll draw a picture of the spectrum. Let's see. So this is going to be a picture of spec of the Laplacian of x. This is 0, and there is going to be an eigenvalue there. So that's lambda 0. And there are infinitely many eigenvalues, discrete eigenvalues, lambda 1. So less than or equal to, less than or equal to lambda 2. And then their spacing is not uniform necessarily. Dot, dot, dot. The eigenvalues can coincide, like lambda 1 could be equal to lambda 2. That means that lambda 1 has really multiplicity, at least 2. But overall, they have to tend to infinity. So lambda I goes to infinity as I goes to infinity. And in this case, the spectral gap, okay, there are many spectral gaps, right? There's a spectral gap between every, potentially between every pair of eigenvalues here. But the spectral gap I'm interested in is the one between lambda 0 and lambda 1 if it exists. This time it's lambda 1 minus lambda 0. And just as for graphs, this is equal to 0 if and only if x is disconnected. And it's also true that the spectral gap, same as for graphs, it quantifies the connectivity of x. I'm not being precise about how you measure connectivity, but there's a natural way to do it. You try to divide the x into two parts, each not too small in volume, by a hypersurface with small area. How hard is it to do this? So that's results of Cheeger and Boozer. And also the rate of exponential mixing. This time, for graphs, it was exponential mixing of the random walk. Here's exponential mixing of the geodesic flow. On T1x. So just as for graphs, the spectral gap on the surface gives you, has interesting consequences that are actually, they have useful applications. So it's also, okay, there's also some situations where you want to maybe have, for theoretical applications, to have a surface with a large spectral gap. Are there any questions so far? But please feel free to interrupt me if there are questions. So now that I've introduced spectral gap, I want to go a bit further. So the real theme of the talk is how common is it that like an object will have a large spectral gap? is large spectral gap the typical behavior or not? So, okay, this is very vague. More precisely, if I pick a random graph or a random surface, how large is the spectral gap? So this question was actually very popular in the context of graphs, and much work has been done on it. For surfaces, okay, it's been around for a while, but I'd say it's like becoming a hot topic right now. The person who really kicked this off was Magee in recent years, but the work goes back to Brooks and Rockover. Okay, so I'm interested in the spectral gap of random surfaces, but lots of work has been done about random graphs, so I'll talk about that first, okay, because it's going to tell us what we should expect about surfaces. So let's talk about random graphs. Okay, so my graphs are going to be d-regular graphs on m vertices. And like I said, so it's useful to have a graph with d fixed, n is large, and having a large spectral gap. In other words, what does large spectral gap mean? It means lambda 1. I want lambda 1 to be as small as possible, right? But actually, it turns out that there's a fundamental barrier on what you can achieve, how small you can make lambda 1. And this is given by a theorem of Laplacian and Laplacian. So it says that if G is a d-regular graph, on n vertices, then lambda 1 of G can't be any smaller than 2 root d minus 1 minus small o of 1 as n goes to infinity. Okay, so this is putting a limit on what you can achieve with spectral gap. Asymptotically, you cannot do, asymptotically as n goes to infinity, you can't do epsilon better than 2 root d minus 1. Okay, so this 2 root d minus 1 is called the Ramanujan point. So I'm not actually going to explain why that is, but it's related to, okay, Lebowski-Phillips-Arnack construction of Ramanujan graphs using Ramanujan-Peterson conjecture. But there's a more basic reason why you see this number. So what is the number 2 root d minus 1? This number is the spectral radius of the adjacency operator on the universal cover of G. Okay, spectral radius in the L2 sense of the adjacency operator on U, where U is the universal cover of G. So U is also, I mean, you can say what this is, it's a d-regular tree. All right, so in our quest for a big spectral gap, we're not going to be able to do better than lambda 1 is 2 root d minus 1, maybe minus a small bit that goes to 0 as n goes to infinity. Well, actually, the conjecture is that typically you do get very close to this, and that's the generic behavior. So this was a conjecture due to a law that was proved by Friedman. It says for any epsilon bigger than 0, asymptotically almost surely, which I'll explain this concept momentarily, a random d-regular graph G on n vertices has lambda 1 of G less than or equal to 2 root D minus 1 plus epsilon. And I'll explain what asymptotically almost surely means. Asymptotically almost surely, which I abbreviated by AAS, it means it happens with probability tending to 1 as n goes to infinity. So, put another way, this theorem of Friedman says that random deregular graphs have almost optimal spectral gap. And almost can be as small as you want, but fixed. I want to go a bit deeper into this random graphs because it's helpful. You might notice that I didn't tell you what it means to pick a random deregular graph on n vertices. The natural way to do it is, well, there's a finite number of them, so pick each of them with equal probability. But actually, sometimes it's useful not to use that random model, but to use a slightly different one. So there's actually a result called contiguity, which is a result of Doron. What it tells you is that it's not really important for this talk, but it tells you that you actually have some flexibility. So it says if you want to prove a Lawn's conjecture, okay, and you don't, okay, it's already been proved, but if you wanted to prove a Lawn's conjecture, you have a priori flexibility in what random model you use. In proving a Lawn's conjecture, there's a priori flexibility in the random model. I'm going to be more concrete now. So what other random model of deregular graphs might you want to use? Well, for example, if you accept that D is going to be even, then a 2D regular graph on n vertices is a degree n topological cover of the following graph. Yeah, it's a degree n covering space of this. Okay, there's supposed to be D circles, but here I made D3.
Degree n, right?
Yeah, thank you. Okay, it's not clear right now why that's a useful perspective, but it is. It's the perspective. It's a perspective that carries over nicely to surfaces. But I do want to mention one more thing. So if you now take this perspective that this is going to be a random model, we'll pick a random covering space. Well, why start with this graph, this bouquet of circles, and not some other graph? And yet people did ask this. Friedman asked this question. So it was a conjecture of Friedman. Oh. That's been proved recently by Collins and Wardenav. What is this thing that they proved? a natural extension of a Laplace conjecture to random covers of any fixed graph.
So if you don't have a bouquet of circles, sometimes people call it random lift graph, no?
Yeah, random. But there's funny, so yeah, lifts in combinatorics for covering spaces. So,
yeah.
So I don't want to use that language because it's confusing.
Sure.
But then covers or something else. So it's yeah, not random lift graph. So
I think there's also a model of random knots where which starts with a bouquet of circles and then you put some kind of matching or something like that. So this is called Petaluma model or something. So there are similar pictures. It's a possible way of putting some sort of probability measure on the space of knots. But anyway.
Yes, it sounds interesting. Maybe we can discuss. There's two subtle points about this extension of the Laplace conjecture, though. The first one is not that subtle, actually. It's just that I'm just going to say them, actually. So there's one problem, which is like any eigenvalue of the base graph will also be an eigenvalue of any cover. So you have to exclude them from the conjecture because they'll always be there. Okay. So when you have a covering space, you have a concept of new eigenvalue, which is an eigenvalue that's in the covering, but it occurs with greater multiplicity than it did in the base. So this extension is about new eigenvalues. The second thing is natural, but you have to replace the number 2 root d minus 1 by something. So I'm going to write this. So 2 root d minus 1. But it's because of what I said before, it's clear what it should be replaced by. It's replaced by the spectral radius. Let me just fix this. Let's call the base graph G0. So here's G0. Replaced by spectrum, spectral radius of AU, U equals the universal cover of G0. All right, so I think I've said everything I wanted to say about graphs to motivate what I'm going to say about surfaces. So, okay, my model I want to use of random surfaces is random covers, also random covering spaces of surfaces. I'm going to say covers when I mean covering space throughout the rest of the talk. Okay, so that's very good, but I said that the perspective of random coverings is helpful. So now let me explain why in the context of surfaces, and also explain the construction of a random cover of a surface. So random covers of hyperbolic surfaces. Okay, so let's start with our base hyperbolic surface, H mod gamma. It'll be connected, that's fine. Connected, compact hyperbolic surface. And I'm going to work with symmetric group, Sn. So it's the symmetric group of permutations So it's the group of permutations of the numbers 1 through n. And I'm going to explain that there's a correspondence between group homomorphisms from gamma, which is the fundamental group of X, to the symmetric group on one side, and degree n covers. So cover is a covering space. Covers of X. And these covering spaces are Riemannian covering spaces. So they respect the metric and the Laplacian and the measure and everything. It's going to take the form of, given a homomorphism, a group homomorphism, I'll build a surface which is called X phi. And this will also have a covering map to X. And this is actually going to be a one-to-one correspondence. But there's a minor technicality, which is that it only becomes one-to-one after I remember some extra information on the cover. I'm not going to go into this. It's just a bit of extra decoration. Then this is one-to-one correspondence. Label degree n covers of X. Okay, so I'm going to now start with a homomorphism and I'm going to build the surface. How do I do it? Well, X phi is going to be a quotient space. So this is my definition. It's going to be a quotient of gamma acting on some set, but that action is going to depend on phi, my homomorphism. And my set that I'm acting on is the product of the hyperbolic plane with numbers 1 to n. Another way to think about this product is just n copies of the hyperbolic plane. And the action of gamma on this product, so it's acting on a pair zi, where z is a point in the hyperbolic upper half plane and I is a number between 1 and n. Well, gamma just acts on z as it knows how to by a Mobius transformation, and it acts on I through phi. And that's it. So okay, so people may recognize this construction as an example of a fiber product. So this is what it is. It's a fiber product. Well, okay, so what do you get out of this? Well, this set of homomorphisms from gamma to Sn, it's actually a finite set because gamma is finitely generated. So you just have to, yeah, I mean, at most you're choosing where the generators go in a finite group, Sn. So phi's live in a finite set, so you can choose them uniformly at random. Hom gamma Sn uniformly at random. And if you do that, you'll obtain X phi is a random degree n cover of X. Okay, so these are our random surfaces. What do we know about their spectrum, their spectral gaps? So this is the main theorem of the talk. So this is joint work, as I said, with Frédéric Naud and Doron Puder. Okay, so it's the same setup as the previous page, which is that X is a connected compact hyperbolic surface. So for all epsilon bigger than 0, asymptotically almost surely, which has the same meaning as before, means that it happens with probability tending to 1 as n goes to infinity. Here n is the degree of the cover. The spectrum of the Laplacian on X phi in the region 0, 3/16 minus epsilon is the same as the spectrum of the Laplacian on X in this region. So the fact that I can't just say that, you know, the fact that I can't give an explicit spectral gap is the same issue I mentioned before about new eigenvalues. So like any eigenvalue of X in this region has to appear here. Okay, so the fact that I have to have these elements is forced upon me. It has to be there. It does give you a uniform spectral gap for the X phi, because X itself has a gap between its lambda 0 and lambda 1. So it's saying that the X phi asymptotically almost surely have a uniform spectral gap of either 3/16 or the gap between the first two eigenvalues of X itself. But you might not like that. You might not like this, but if you don't like it, then there's a way to get around it. I mean, what I'm saying is you might want to just actually have a spectral gap of size 3/16 minus epsilon. So you can do this. So why? Well, you can choose carefully the X that you start with. So there's a result of Jenny. It tells you that there exists a genus 2 hyperbolic surface X with lambda 1x bigger than 1/4. So if you start with this X as your base surface, then the only thing you'll see on the right-hand side is 0. Okay, and then you really get a spectral gap of size 3/16 minus epsilon for the random cover. By the way, part of the motivation for this work is that it's unknown whether there exists a sequence of compact hyperbolic surfaces with genus tending to infinity, such that lim inf of lambda 1 is at least 1/4. In other words, it's definitely not true that Jenny's result is known in arbitrarily high genus. So okay, so this is new construction of surfaces with large genus on large spectral gap. Previous constructions use number theory in a essential way. I'll actually come to this point now. So there's an interesting coincidence, maybe more than a coincidence, but not sure at the moment. The theorem of Selberg is actually about non-compact surfaces, but it can be made by a trick into a theorem about compact surfaces. Okay, so it says if you let gamma of n be the kernel of reduction modulo n, on SL2Z, and you let x of n be h mod gamma n, then Selberg proved that lambda 1 of x of n is at least 3/16. Okay, so like I said, I don't have an explanation about why the number appears in these two different theorems, but it's interesting.
Michael, I wanted to ask, so you were saying that there is a recent result on graphs that you don't have to start with a regular graph and you would still have a similar result, right? How about something like this for surfaces? So suppose we start on the base surface, we don't put a hyperbolic metric, but we put something else. Then we can lift it to the universal cover. If it's not too far from hyperbolic, at least we would know that, let's say, continuous spectrum wouldn't move too much or something. So would it be would your methods say anything that maybe, you know, it's not 3/16, it's a bit smaller, but there is some kind of spectral gap for the random lift, not of a hyperbolic surface, but of a surface with a different metric?
Okay, so when we deal with compact surfaces, we use the trace formula. Okay, so that doesn't carry over. But in my earlier paper with Frédéric, when we did convex co-compact, we use transfer. We can use transfer operator machinery as well. So if you had like, if you perturb to have pinched variable negative curvature or something, and you can still set up transfer operators, then possibly yes, but not without serious work.
There is some kind of variable curvature trace formula which is not exact but accurate. You know, we had it in some paper with Josip Polterovich Antov a while ago, but I'm not sure if it's good enough for your purposes. But anyway, I can send you a reference. What
I'm saying is that I don't think the trace formula is essential, because in the case of convex co-compact infinite volume, we didn't have it.
Right.
We did use something special, but no, the method is very robust. I'm going to outline the method. The idea is simple, so yeah, I mean, yeah, it sounds interesting and doable, but not just directly from our methods. Like. Okay, so did we win? Is 3/16 what you're supposed to get? Well, no, unfortunately. So what are you supposed to get here? What is the right number supposed to be? Well, we saw that for graphs, you look at the universal cover, and you look at the analog of the adjacency operator on the universal cover. So to do this just quickly, what is the spectrum of the Laplacian on the hyperbolic upper half plane? There's none below 1/4, so that's the magic number. And then there's absolutely continuous spectrum from 1/4 to infinity. Okay, so I'm not giving any rigorous justification for this, but this 1/4 is the right number. Okay, so that's what it should be. So conjecture. So I think we wrote this down. It should be that theorem 3 holds with 3/16 replaced by 1/4. But it's not really, is this also what Selberg did? And this is a very famous conjecture. Theorem 4 holds with 3/16 replaced by 1/4. This is still open. World record is 975 on 496. Kim and Sarnak. Okay, what else have I got to say? Well, okay, what I really want to do is just to give a sketch of the proof, like just to show the ideas. But firstly, I have to mention some related works. So we weren't the first people to think about spectral gap of random surfaces. So some earlier works were by Brooks and Backover. For a combinatorial model, of random surface, random compact hyperbolic surface, now this model is not quite as clean as our model. In this in this random model, there's a parameter n that goes to infinity. And basically the genus of the random surface will be roughly growing with n, but it's not deterministic. I just want to point this out. So in this model, you don't know exactly what the genus even is. In our model, you do, because it's a degree n cover, something fixed, and the Euler characteristic multiplies by the degree of cover. But what they did manage to prove was that asymptotically, almost surely, as their parameter goes to infinity, lambda 1 of, let's call their random surface x Brooks Mach over n, lambda 1 of their random surface. N is some parameter, which, it roughly speaking, governs the size of the surface. X Brooks Mach over n is greater than or equal to a constant bigger than 0. But C is not explicit. And then also important work of Mirzakhani that Dima mentioned. If X V Peterson G is randomly chosen, with respect to the V Peterson volume form, on moduli space, this is quite long, moduli space of genus G hyperbolic surfaces. Mirzakhani proved that asymptotically, almost surely, this time as G goes to infinity, lambda 1 of this V Peterson random surface is bigger than something explicit but quite small, so 0.0025. I can't round it up because it's an inequality. Okay. 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 So this is the previous, probably best explicit result for random surfaces. Okay, so now let me do a sketch, just the main ideas of the proof. So, like I said, we use Selberg's trace formula. I'll explain very, very roughly what Selberg's trace formula is. Selberg's trace formula. Now you have two things that you could use Selberg's trace formula on. You could use it on the cover, x phi, or you could use it on x, and we're going to do both. But let's do it for x phi. Now, I'm not going to write this down precisely because it takes a long time, but you have an analytic side to the formula, and you also have a geometric side. The analytic side is the sum over lambda and eigenvalue of x phi. I don't really mean it's an eigenvalue of the Laplacian of x phi, but the eigenvalue of x phi, some function f of lambda. And on the geometric side, you have a sum over gamma in gamma, some function g of gamma, and then you have something a bit more complicated. So you have the number of fixed points of phi of gamma. Now, f and g are related by a Fourier type transform. So f and g are strongly coupled. I mean, they determine each other. And they're carefully chosen. This is a kind of standard game. Now, what are we trying to do? We're trying to stop there from being certain eigenvalues, right? There's some lambda on the left-hand side that we don't want to have. So what we're going to do is we're going to set up the analytic side as follows. We want f to be greater than or equal to 0, always. So every eigenvalue contributes something non-negative to the left-hand side. And we're going to want f of lambda to be large if lambda is an eigenvalue that we want to forbid. In other words, we're trying to make the contributions of the things we don't like on the left-hand side large, and then we're going to try to bound the right-hand side. Okay. But we also, there's some, okay, so like I said, f and g determine each other, so that there's a contest. But you can make sure that g is localized. G localizes to gamma with word length with respect to standard generators in the group less than or equal to c log n where c is a constant depending on x. So, like, I haven't given all the details. Obviously, it's more complicated than this, but roughly speaking, you're trying to do this. Okay, so what can you do with this? This was the trace formula for x phi. Now, I have about 4 minutes left, I think. This is not exactly the trace formula for x phi. This is the trace formula for x phi plus some clever observation about how you relate geodesics in the covering space to geodesics in the base, together with the number of fixed points of monodromy around that geodesic. You can also think of this version of the trace formula in terms of flow K theory and a vector valued version of the trace formula. So it is, okay. But what you can also do is you can write down the Selberg trace formula for x and then take the difference of these two trace formulas. This has a very nice effect. It restricts the summation on the left-hand side to new eigenvalues. So if you subtract the trace formula for x, you actually get the following: sum over lambda a new eigenvalue of x phi, f of lambda. Okay, so taking this difference, just left the new ones. And on the right-hand side, what does it do? Well, I mean, part of this is like glossing over some details, but let's just lie a little bit. You get g of gamma, and then you just take away 1. Okay, so it's the number of fixed points. Of phi of gamma minus 1. Now that may seem like it's not going to be helpful at all, but it actually is. So we've done this kind of amplification on the left-hand side, and now I'm going to take expectations. So I'm just going to get an expectation of the left-hand side, but I can move the things on the right-hand side that depend on phi are only the number of fixed points minus 1. So I'm going to take the expectation. My expectation is taken over phi in Hom gamma Sn, sum over lambda nu f of lambda is equal to the sum over group elements gamma and gamma, whatever this function g was that I wasn't really precise about, and then the expected number over phi of the number of fixed points of phi of gamma minus 1. Now, I don't want to run out of time, so I'm going to go through this quickly. The conclusion, if we can get there, is bound to the right-hand side and use Markov's inequality. To forbid eigenvalues asymptotically almost surely. What I'm saying here is that if you can sufficiently bound the right-hand side of this, then the conclusion is kind of just standard probability argument. Okay. So how are we going to get something good for the right-hand side? The idea is, it goes back to Broder and Shamir, who gave one of the first bounds for lambda1 of a random deregular graph using a similar method, is to split the gammas that you saw over here into 3 different groups. So 3 groups of gamma. Idea for bounding the right-hand side. 3 groups of gamma. The first group is, let's give this a name as well, call this star. If gamma is the identity, I can tell you what that is, because 5 gamma will always have n fixed points. Star is n minus 1. If gamma is equal to gamma naught to the q, where q is at least 2, gamma naught is not the identity, then it's actually okay to put a trivial bound in for star. The trivial bound is less than or equal to n. Like no homomorphism, no element of Sn can have more than n fixed points. I'm just about to finish. I'm sorry if I'm going over time. I think I started a few minutes late. This will be the last line. The reason that it's okay to use a trivial bound for these gamma is that there are relatively very few of them. There are exponentially few of these. So these are the gammas that are a proper power of another element. So for these, use a bad bound on star, but there are very few. Now the main innovation is that if gamma is not a proper power, star is O 1 over n. So this is a result of me and Puder this year. But in the original paper, by the way, the proof of this is 64 pages of topology and representation theory. In the first paper proving this, O1 over n as gamma is fixed and n goes to infinity. Yeah, the big O may depend on gamma, so some extra work has to be done to allow gamma to go up to having word lengths constant times log n and still having this. But the point is, actually these gammas that are not a proper power, they're the generic terms on the right hand side, and on these ones you get a big gain from the expectation. Okay, and this is the outline of the argument. So I'm sorry if I went over, and I want to stop here. Thanks for your attention.
Thank you very much, Michael. Are there any questions? So what can you say about the variance for the number of fixed points for generic elements, right? Or the situation, or
the variance for the number of fixed points of a particular element over.
Oh, Yeah, no, I don't know. So how is the number of fixed points kind of, is it tightly concentrated or, but
okay, so like,
I understand that since the expectation was fairly difficult, I think it may be even more difficult for the variance, but maybe.
No, it's actually not. Like, so
Okay.
we can do all mixed moments.
Okay.
But it's error terms that, okay, yeah. We can do all mixed moments and get the first, I'm pretty sure we can get all the first order, like the asymptotic ascending goes to infinity, what the leading order term will be for any mixed moment. We debated doing this in the paper, but the paper was already very long.
Mm-hmm.
Yeah, it's like we need to write this down because everybody else will. Okay, yeah. So I think it's not out of reach if someone needs the results.